the unique challenges of answering this type of question in the context of environmental policy and climate policy. So we have misaligned data when you're thinking about data about climate stressor with health data. They are measured at different spatial resolution. We have data on all of the possible diseases that it would be silly to treat them one independent from the others. All of the diseases are correlated. We have a multimodal data. I'm going to show you that we have data from satellite, from electronic medical record, from sensors. This data that varies space and time. Of course, this is why the causal inference come in. There is spurious correlation, there is confounding, they are massive, and the causal effect are hard to detect, right? So you will expect that if you're breathing pollution every day, you're not going to get an enormous impact on health outcome, although the impact is there. So that means that when you're thinking about machine learning, and then I'm going to get to the journey of AI, interpretability, reproducibility, responsibility, and accounting for uncertainty are not negotiable, right? If you want to develop these tools to impact policy, these are criteria that you have to think about. So let me first talk about a simple, I would say, approach to think about machine learning and artificial intelligence, which actually interpretability is not an issue yet. One of the challenges that we need to focus is the fact that we need to estimate exposure to air pollution for every single individual in the United States of America in the last 20 years. This is the map in the United States that shows where pollution is measured every day. So you see that there are several thousands of monitors. However, there are areas in the United States where it's not monitored very well. So now this is a task which machine learning methods can do really, really well. And that's actually, there is an enormous literature. I will encourage you to look at it. But basically you can think about tree-based method, neural network, and we have been using ensemble and hybrid methods, where basically you take information from satellite information, so aerosol optical depths from satellite, or I'm sure you are familiar with imaging data, merge with monitoring data, merge with land use data, merge with the output of atmospheric chemistry model, and you can estimate at very high resolution, 1 kilometer grid exposure to air pollution. If you're interested in this field, which of course there is always more and better that we wanted to do, I just want to mention one paper that you might want to look at. This is not my work, it's with my dear colleague Marianti, and I cannot pronounce her last name, but you can see it there because it's too long. But my dear colleague Marianti, she has been developing these models where the focus is really, because this is an uncertainty in AI conference, I wanted to point it out, the really important piece where they're developing machine learning model that can estimate and downscale exposure to air pollution, but also quantify the uncertainty. And they're quantifying two types of uncertainty. They're quantifying the uncertainty in the model, in the machine learning model, and they're quantifying the uncertainty in the parameter estimation. Again, when I'm talking about changing policy, quantification of uncertainty is key, right? So in these are, I call it straightforward model, because there is nothing about causal inference. This is about combining spatial, temporal, multimodal data using machine learning or ensemble learning to get the very good downscaling. There is still a lot of work that needs to be done, but also I think this is, one of the most exciting work, the start to quantify the uncertainty with exposure prediction. So we have been using that approach, and then we have been able now to quantify the 1 kilometer grid exposure to air pollution for every single older American in the last 20 years, right? So we have all of the longitudinal data on health, and now we have the output of this machine learning model that gave us the exposure to air pollution. By the way, all of this data is publicly available if you're interested. So now let's go to the second topic. which is causal inference. And so how we start thinking about what is the history of doing causal inference in artificial intelligence, and how we're exploring the potential outcomes for decision making. So I wanted to be explicit here that there are generally two framework for doing causal inference, right? Which actually I think that as I was more learning about the Judea-Pearl framework is broader and encompasses actually the potential outcome framework. But I want to be explicit about it, that there is the potential outcome framework, which is basically the Rubin framework, where estimate the effect of a pre-specified interventional time, thinking about approximating a randomized experiment, focusing on estimating average effect, and is designed for targeted specific causal inquiries, where the causal graph model can model and analyze multiple intervention and causal pathways, identify confounders, facilitate the discovery of new causal relationship, and its idea for exploring complex interconnected causal structure. What actually I've decided to do, instead of start to distinguishing between the potential outcome and the causal graph model, I decided to frame the statistical journey from statistics to artificial intelligence, as I mentioned before, within the Pearl causal framework. And so with the orange association, sorry, with the red, with the red association with the orange, with the interventional, and with the green, the what if. So that's what I'm going to walk through in the next 20 minutes. So I think when you're thinking about analyzing this massive amount of spatial temporal data under a causal framework to impact policy, this is the evolution that me and many of my colleagues have been thinking about. So first, if you think about in the late 90s, before causal inference, right? Everything was basically seeing, right? Estimating association, but even before causal inference, there was a lot of work that, especially in the Bayesian community, was seeing with uncertainty. And so basically it was both Bayesian regression models that account for the uncertainty in the parameter, and Bayesian model averaging, which also account for the uncertainty in the model choice. Then in the later in the early 2000, now we start thinking about Bayesian causal inference. Both Bayesian causal inference in a parametric way, which I'm going to tell you more about, and also in a Bayesian causal inference in non-parametric way. In fact, yesterday, for whoever took the course of Mike Daniels and Jason Roy, that's exactly what they are talking about. And now in 2023, back to 2025, there is now the AI, where we are thinking about basically the imagining world and foundation model. And then I'm going to talk about what happens if you now start to layer in the uncertainty on the foundation model, and then start to think about the future in 2050. Okay, that is a little bit in a very simplistic way what I'm going to talk about the different approaches. So one of the ideas that I thought that started a new area of research into basically Bayesian causal inference accounting for the uncertainty was this work that I co-led with one of my former PhD students of mine. This was in 2012, and it was the idea of a Bayesian causal inference accounting for confounding. So this is part of the doing, because the goal was to estimate, let's see if that works. Yes. Our goal was to ask the Pearl question, what will happen if I change the value of X? I have confounders U, right? But the uncertainty piece of this model was based on these parameter alphas. These parameter alpha were unknown parameters, which were 1 if that confounding variable will come into the model, and were 0 otherwise. So just think about that. This is representing a large class of causal graph, right? because depending on these values of alpha, you will decide which causal graph you are considering, because which confounders are confounders. Now, what was the key idea, the innovation that opened an entire area of research on Bayesian causal inference was the fact of this value omega, which will be the odds of including a confounder, what we call it the outcome model, if this is a variable that predicts the exposure variable or the intervention variable. This one is also, you can call it the propensity score. And we said that we set this value that should be really high. And the idea is you're gonna include a confounder, what the idea is, if a variable u is a strong predictor of the exposure or the intervention, then the probability of including the same variable in the outcome model must be very, very, very high. And that was the first idea that accounts for the uncertainty in the confounding adjustment versus accounting for the uncertainty into the predictor of a model. This started a new era of